Okay, class, we're about to start section 2.2. And as you see here from the syllabus, we're covering pages 123, 125, 127, and 130. And it also has the problems we're supposed to cover. Now, going to page 123, lesson 2.2, 88 miles per hour. Our learning objectives is compute rates of change and compare it to ratios and conversion factors. And we're also to interpret and use rates of change and convert units involving rates. Okay, now, if we go down here to the bottom, it says a rate is a ratio that compares two quantities. By rate of change, we mean a rate that compares the change in one quantity to the change in another. A speed like 88 miles per hour qualifies because we can write it this way: 88 miles divided by 1 hour. This quite literally compares a change in distance, 88 miles, to a change in time, 1 hour. We call it a unit rate because its denominator is 1. Now, for number 1, it says list some unit rates you're familiar with. Okay. So 1, we could say 60 miles per hour, per 1 hour. Or we could say 50 cents per gallon. Or another famous one is I make $15 for 1 hour. So those are some unit rates that we are familiar with. Now, when we look at problem number 2, it says list some rates that aren't unit rates. So, if we made $100 for 8 hours of work, remember a unit rate must have 1 in the denominator. Or we traveled 240 miles in 4 hours. That is still not a unit rate. And then finally, if we made $1, we're going 0.25 miles. So these are not unit rates. They are rates, but not unit rates because they're not divided by 1. Now it says here, compare rates of change and conversion factors, which we studied in lesson 1.5. How are they similar? How are they different? Okay, they're similar because both are fractions. Comparing two quantities. And for example, or we could put like 88 miles over 1 hour and 12 inches for 1 foot. Now, the difference is, and we could put but in a conversion factor, the two quantities are equivalent. And in the rate of change, they are not. Because remember, when we did conversion factors back in 1.5, the main thing that we stressed was that they actually equal to 1 because they were equivalents of each other. But when we're dealing with the unit rates, they are not equivalents of each other. Just like $100, just like up here with number 2, $100 and 8 hours are not the same thing. They do not divide out to actually 1. So that is the difference. Now, we move on here to number 4. it says, let's explore the idea of rates of change as a comparison between changes in two quantities a little more. According to the U.S. Census Bureau, about 2.7% of registered nurses in 1970 were men, compared to 9.6% in 2011. In 2011, the average salary for male nurses was $60,700 per year, while the average annual salary for female nurses was $51,100. How much did the percentage of male nurses increase from 1970 to 2011? So, if you look here, it was 6.9%. Now, just to let you all know where I got the 6.9% from, off to the side, in 2011 it was 9.6%, and in 1970 it was 2.7%. And when you subtract these two, it'll give you 6.9%. That's where I get the 6.9%. But now we would take 6.9% and divide it by, we go from 1970 to 2011, that's 41 years. So when we put this in our calculator, now what I would suggest you do, when you put this in your calculator, you would just take 6.9, don't change it to a decimal, just leave it at 6.9 divided by 41. And this will give us approximately 0.168. So we will simplify this down to 0.168 and divide it by 1. Because once you put it in the calculator, whatever value you get, this value is divided by 1. So basically, and we could put a percent sign, this would equal to or be approximate 0.168% per year. Okay. So, to describe what happened here, we would actually, I actually went a little bit above and beyond on this problem. So let's backtrack here. I made a little error, but this was the actual answer for number 4, the 6.9%. For number 5, it says how many years passed in a time frame, which was that 2011 minus 1970, which is 41 years. Okay, which we had up here. And then number 6 asked us to do the division. So it'll be the 6.9% that we got here in problem number 4 divided by 41 is equal to 0.168% divided by 1. Remember, we got that in the calculator previously. So it's approximately 0.168% per year. Okay, now, and then they want us to tell what does this answer tell us. So basically, the percentage of male nurses increased on average 0.168% each year. This is the rate of change which compares a change in percentage to a change in time. Because up here we have percent, I should have put years here. And then 1 year here. So that compares a change in percentage to a change in time. Okay, now we move on to number 7. It says find the rate of pay for women compared to men in 2011. Write your rate so that it has $1 in the denominator. So we want to find the rate of pay for women compared to men in 2011. The average pay for women were $51,100. Average pay for male nurses was $60,700. Now when we put this in our calculator, 51,100 divided by 60,700. You notice that we have 0.84. We can round this to 0.84 because remember, for most things, the value of our money goes only to 2 decimal places. So it'd be 0.84 over $1. Now, we move on to the next page, to problems 8 and 9. Now, with problem number 8, it says, what does your answer to question 7 tell you about the gender gap in pay for nurses? What do you think is responsible for the discrepancy in earnings? So, female nurses make about 84 cents to every dollar a male nurse makes. There are actually no good explanations because women do the same job as men. Okay, number 9. Explain why your answer from question 7 is not a rate of change. And the reason why it's not a rate of change is because it's not comparing two different quantities. It's comparing basically the same quantity. So it compares two salaries, not two changes in salary. So now we move on to the second part of our homework or classwork. It says the word equivalent is an important word in math and one that we'll use often in this course. Make sure you clearly understand what that word means. Look it up and discuss it with your group if necessary. If you make $100 a day for doing a certain job, how much money would you make in a 5-day work week? Okay. So what we would do, you made $100 a day times a 5-day work week, you would make $500. Now number 2, our $100 divided by day, and it's supposed to be divided by 1 day, or you could just leave it as day, and $500 for 5 days equivalent rates, and it's yes. Both reduce to the same rate per day. Okay, now Going over to page 126. It says, question 2 demonstrates a useful fact about rates of change. They can be scaled up or scaled down to fit a given situation. Scaling up a fraction is done by writing an equivalent fraction, that is, one that has the same value, using larger numbers. Scaling down is writing the equivalent fraction with smaller numbers. These processes are done by either multiplying both the numerator and denominator by the same number or dividing both the numerator and denominator by the same number. It says here for number 3, write a fraction equivalent to 60 miles over 4 hours that has 2 in the denominator. So 60 miles over 4 hours. We want to get 2 in the denominator, so we ask ourselves, what do we have to do to 4 in order to get 2 in the denominator? And that would be to divide it by 2. And whatever we do to the denominator, we must do to the numerator. So that'll give us 30 miles over 2 hours. And that's what we were stopped at. Okay, number 4. Write a fraction equivalent to 60 miles over 4 hours that has 1 in the denominator. So we add 60 miles over 4 hours. And to get this denominator to equal 1, we have to divide the numerator and denominator by 4. So that would give us 15 miles over 1 hour. Now number 5. Write a fraction equivalent to $320 for 4 days that has a 10 in the denominator. Hint, first scale down, then up. Okay, we add $320 over 4 days. Now that would be a wise thing to do, is to take the denominator down to 1 or even down to 2 and then go to 10, because 4 doesn't go evenly in a 10. So we could divide the numerator and denominator by 4. This would be $80 over 1 day. And then we can multiply the numerator and denominator by 10, and it would be $800 for 10 days. Okay, now for number 6. It says if one bicyclist is pedaling at a rate of 40 miles in 3 hours and another at a rate of 50 miles in 4 hours, which is faster? Scaling either up or down can be used. So it's 40 miles for 3 hours. So we could divide each by 3, and then we have 1 hour in our denominator. And if you take your calculator and divide 40 divided by 3, that'll give you about 13.3 repeating 3. And that'll be 13.3 repeating 3 miles per hour. So now we would take 50 miles divided by 4 hours. We could divide both by 4. And that would give us 1 hour in our denominator. And that would give us 12.5 miles in our numerator. So this one here is faster. And we're done. Okay, now we move on to number 7. It says most experienced runners get to a point where they can comfortably jog long distances at a constant pace. This pace, of course, is another way to say rate of change, because speed is the rate at which distance changes compared to time. One particular runner jogs 1 lap around a 400-meter track in 2 minutes. In questions 7 through 15, you can assume that the runner can maintain this pace for a long time. So for every 2 minutes, the runner jogs 400 meters, as according to this chart over here. Okay, now, and according to the directions. It says complete the table, continue the pattern for times, and finding the associated distances for this runner. So basically what they're saying is this runner is going to keep up the same pace. So let's complete the table. So basically we doubled this time here. We have to double this distance here. If we make this 6 hours, we would triple the initial 2 minutes to 6. So we have to triple the initial 400 to 1200. Then if we go 8 minutes, we would take 2 times 4, which gave us 8, and 400 times 4, which would give us 1600. And then so on. This would be 10, so we'll multiply that by 5. And then this would be 12, and we'll multiply this value by 6. All right, number 9. Notice that the rate at which the runner's distance changes is constant. When the rate of change is constant, a quantity illustrates what type of growth that we encountered in lesson 2.1. When it's constant, it's typically linear. Write the runner's rate as a fraction using meters in the numerator. So if we had 400 meters divided by the time, which would be 2 minutes, and they did not ask us to simplify, so we're basically done with number 10. It says 11, write this rate as a unit rate. Now this is where we would have to simplify. So we have 400 meters over 2 minutes. We have to make this denominator 1, so we have to divide the numerator and denominator by 2. And by dividing them by 2, this will give us 200 meters over 1 minute. Now we're going to write this how it's usually presented. Instead of writing 200 meters or leaving it as 200 meters over 1 minute, it's usually 200 meters per minute. You typically do not have to write the 1. Now we go here to number 12. It says convert your rate from question 11 to meters per second using dimensional analysis. Now we have 200 meters over 1 minute. Now we're putting this here because we're using dimensional analysis. So we want to change this to seconds. So we know for 1 minute there are 60 seconds. So we needed to put minutes in the numerator because we're trying to get rid of this minutes out of the denominator. So minutes will simplify each other out. This will be 200 meters over 60 seconds. Now when we simplify this to make this a unit rate, it's going to be approximately 3.33 meters per second, because they asked us to round to 2 decimal places. So it'll be an approximation. Now, we go over here to problem 13. Now problem 13, it says, what distance will the runner cover in 40 minutes? So we would take our 40 minutes and multiply it by 200 meters for every minute. The minutes will simplify each other out, and we'll have 8,000 meters. Okay, now it says, what distance will he cover in 40 seconds? Now we will have our 40 seconds. And remember, in the previous problem, we found that 3.33 meters is how much is covered in 1 second. And that was actually in problem number 12. So the seconds will simplify each other out. 40 times 3.33 will be 133.2 meters. Now 15, it says, what would this runner's total time be for a 10K race? 10 kilometers, that is. Recall that 1 kilometer is equal to 1,000 meters. Your answer to question 11 will help. Okay, now, first of all, we know we're converting 10 kilometers. We've been told that it takes 1,000 meters to equal 1 kilometer. We were given that. Now, our answer to number 11, we have 1 minute, 200 meters. We just did the reciprocal because it was, as we did in problem 13, 200 meters over 1 minute, and we just did the reciprocal. Remember, we're trying to get how long would it take for a 10K race. So that's why we have the amount of time in our numerator. So kilometers will simplify out, meters will simplify out. Now when we multiply this out, This will give us 10,000 all over 200. And this will all be in minutes. 10,000 over 200 will give us 50 minutes. So it'll take 50 minutes to complete a 10K run. That's if the runner runs at the same speed. Okay, now for 16. As question 15 shows, when dealing with rates, sometimes it's necessary to convert the units in both the numerator and denominator of a fraction. For example, it's common to convert speeds from feet per second to miles per hour. Both feet and seconds need to be converted. Fortunately, dimensional analysis is a perfect tool for this purpose. Because the conversion factors we use equal 1, regardless of which unit is in the numerator. The Earth moves at about 98,000 feet per second as it revolves around the sun. How fast is that in miles per hour? Recall that 1 mile is equal to 5,280 feet. So we have 98,000 feet per second, per 1 second. So now we want to get rid of feet. We want to make this miles. So it'd be 1 mile for 5,280 feet. Now they want our answer in miles per hour. So we got the miles part because the feet will simplify out. Now we need to change seconds so we would get hours. So we can have 60 seconds. It's 1 minute. And then multiply by 1 minute. Well, actually it's 60 minutes, not 1 minute. 60 minutes is 1 hour. Okay, so now we have feet, simplify out with feet. Seconds, simplify out with seconds. Minutes with minutes. So now, when we multiply this out, take my calculator here. We have 98,000 times 60 times 60. So our numerator will be a nice long number here. It'll be 352,800,000 divided by 5,280. And in the numerator, that'll be miles. Denominator, that'll be hours. So now we will divide them. And we will get approximately 66,818 miles per hour. And that is our final answer. Now we come to the last portion of this exercise for 2-2. It says we're supposed to go to page 130 and do problems 1 through 10. Pick 1 or 2 if time permits. So we're going to go to page 130. And I may just pick 2. Okay, so it says when advertising special financing deals, car makers often use rates to describe what your monthly payment will look like. This is because the amount you need to borrow varies widely based on the car you choose and the down payment you make. In January 2013, Hyundai offered 2.9% financing on the Genesis Coupe, which would result in monthly payments of $22.09 per 1,000 borrowed for 48 months. Okay, for number 1, for every $1,000 borrowed, the monthly payment will be $22.09. So if you borrow $2,000, you will multiply 2 by the $22.09. Now it says complete the table of loan payments using your answer to question 1. Okay, so now basically for question 2, this will reveal it. So for every 1,000, we will have to add on another $22.09. So this will be $44.18. This will be $66.27, $88.36, $110.45, $132.54. We have $154.63, $176.72, $198.81, and then $220.90. Because remember, for every 1,000, you have to add on $22.09. So if you go from 1,000 to 10,000, you could just basically take 10 and multiply it by, well, that's actually 100, and multiply it by the 22. Well, actually, it's 10. I'm sorry, it's 10. From 1,000 to 10,000 is 10. So you'll multiply this by 10 and get your $220.90. Okay, number 3, write the rate Hyundai advertised as a fraction. So this would be the last problem that I will complete here. It would be $22.09 payment for every $1,000 borrowed. And that is it.